Okay, so we're looking at page 6 in our packets. These are the word problem variations on the definite integral net and total area questions that we've been looking at. So one thing I wanted to do was remind us of a couple of relationships. One is that the antiderivative of acceleration is velocity, and another is that the antiderivative of velocity is position. All right, so let's take a look at number 12. A car moving with an initial velocity of 5 miles per hour accelerates with a rate of 2.4 miles per hour per second for 8 seconds. How fast is the car going when the 8 seconds are up, and how far did the car travel during those 8 seconds? All right, so my first step in this adventure would be to come up with an acceleration model. All right, so a velocity model. So velocity is, well, it's starting off with an initial velocity of 5 miles per hour. So it's that plus the antiderivative of the acceleration model. All right, that acceleration model is 2.4 miles per hour per second for 8 seconds. So 2.4, and I'm going to include the units here just to emphasize something, namely the units. Miles per hour per second, dt, but dt would also be in seconds, dt seconds. All right, very rarely do we include the units, but since it's a contextual situation, it's worth it in this situation to do so. All right, so the seconds, you see that one is a denominator, one is a numerator, would cancel, and we would be left with v equal to 5 plus the antiderivative of 2.4 miles per hour dt. So the 2.4 dt is going to become 2.4 t. Antiderivative of 2.4 with respect to time is 2.4 t. All right, now this is happening over the course of 8 seconds. All right, the unit of time that we were dealing with were in terms of seconds, because that was the dt component of it. So our definite integral is going from 0 to 8. So I'm going to chuck that in as the boundaries of integration. All right, so we had 5 miles per hour plus another 2.4 t, whatever that is over 8 seconds, miles per hour, which is going to give us the accumulated miles per hour over that period of time. All right, so I can plug in the 2.4, the 8 for 2.4 t. So 2.4 times 8 minus 2.4 times 0. And that's all getting added to the 5, but do that separately. You can do it all on your calculator too. I just wanted to take you through the nuts and bolts of it at least the one time. All right, so 5 plus 2.4 times 8. All right, so 24.2. Those units, miles per hour, are going to carry along. All right, so mph. All right, so that's the first part. Second part is saying how far did the car go during those 8 seconds. All right, so we have a function to represent the velocity at any time t. All right, so v, because even though we use notation for it, it still is what it is. All right, so I'm just going to get my writing implement here. So for part B, we still know that v is equal to 5 plus 2.4 times time. All right. So if I want position, I would need the antiderivative of that. So S would be equal to the antiderivative of 5 plus 2.4 t Now, again, I'm going to emphasize the units here. This is all in miles per hour. And you know what? I'm going to do it the old-fashioned way. Miles per hour. dt. Well, dt could be whatever I want. So if I want it to be in hours, that's fine. But then my bounds of integration have to be in hours. I could also make it in seconds, in which case I'd have to change the notation a little bit. All right, so there's a couple of ways to handle it. I think the easiest way to do it would be to make my dt go in hours so that we get that nice cancellation like we did before, and we get an agreement between our two variables. All right, so the result of this will be in miles. All right, so at least we know the units of our final answer. But I can't say that it's going to go from 0 to 8, because if we're looking in terms of hours, that's not correct. This formula would think that it's 8 hours. All right, 0 seconds and 0 hours are the same thing, though, so I could put that there. All right, so I need 8 seconds is blank hours. Make my blank a little longer. And actually kind of position it somewhat differently. All right, because there are 3,600 seconds in 1 hour. All right, so you can create a proportion if you want to do it. So we know that there are 3,600 seconds in 1 hour. So if I want to have 8 of those, then I could just do the multiplication, or I could say 1 hour is equal to 3,600 seconds. So blank hours would be 8 seconds. And then we just do the cross multiplication, but really it ends up being just a reciprocal. All right, so x would be equal to 8 over 3,600. Now we can simplify, not much, but maybe it'll make it a little nicer. 1 out of 450. One 4/50th of an hour. All right, so that's my upper bound of integration. So the unit conversion is actually the only thing in this problem that makes it somewhat challenging. But we will get a solution. S is going to be equal to, and this one will just crank in the calculator, math 9, 5 plus 2.4, we'll use x, going from 0 to 1 4/50th. All right, so, well, no rounding instructions, so I'm going to say 0.01. I'll say just to give it a little bit of reasonable accuracy, 0.01112. Miles. All right, so the vehicle was starting at 5 miles an hour and accelerated at a rate of 2.4 miles an hour per second for 8 seconds. It never ended up after those 8 seconds going faster than 24 miles an hour-ish. So to say in 8 seconds that it had gone an appreciable distance would be not logical. So like if we got an answer of like 10 miles, I would question the accuracy of it. All right, but this is, I think, pretty reasonable. All right. Huh. Unless I am missing something. Number 13 is an exact duplicate. Am I missing something? I don't think I'm missing something. All right, so that is a typo for somebody. So the first person to submit that to your teacher, I suppose, is going to get a bonus point. Wunderbar. Number 14. Given v of t is equal to 5 cosine of t on the interval of 0 to 2 pi. I just put my pen down for a sec and I lost it. Oh, got it. Determine when the particle is moving to the left, to the right, and stopped. All right, find the particle's displacement for the given time interval and then the total distance. All right, displacement is a net quantity. Total distance, well, the word total's in it, so that should be easy enough. All right, so let's actually take a quick look at the cosine graph. On the interval of 0 to 2 pi. So it's your ordinary cosine graph, just with a little bit more height. All right, so I just have to tweak it. Mine, as many of us know, has a different functionality. But this is generally what we're talking about. All right, so that's what we're looking at in terms of the graph. So determine when the particle is moving to the left, to the right, and stopped. So velocity, if it's only moving to the left and to the right, and that's the assumption that we have to make here, velocity is either going to be positive, 0, or negative. If the velocity is positive, then we're moving to the right. If it's 0, then we're moving, or not at all, so at rest. And if it's negative, we're moving left. All right, positive would be above the x-axis. Zero would be on the x-axis. Left would be below the x-axis. All right, so it's above the x-axis from 0 to 2 pi, 0 to 2 pi, the whole thing is 0 to 2 pi. 0 to pi over 2 is what I meant to say. All right, so on the interval 0 to pi over 2, and also from 3 pi over 2 to 2 pi. It's on the x-axis at pi over 2 and 3 pi over 2. Below the x-axis would be between pi over 2 and 3 pi over 2. So to find my displacement, that's simple. All right, S is our displacement, or net position, which is displacement. All right, so that's something that maybe I can clarify up here. Save you a little confusion down the line. So net position. And total position. Total position is just kind of a weird thing to think about. It's like, how do you total out positions? But that is something that you can do. So if I just want the net, that's the integral on the interval of 0 to 2 pi of 5 cosine t dt. Now, in your calculators, if you have the appropriate viewing window established, you can just hit second trace and then select the one that looks like an integral symbol. All right, I think it's 7. Pretty sure it's 7. But I'm going to do it in my home screen. Because there's a way to do it on here, but I think it's more trouble than it's worth because it doesn't line up enough with the way that you would do it. So I'm just going to use math 9. So 5 cosine x going from 0 to 2 pi. And we get this funky, or I get this funky value, but on your calculator, it should just say flat out 0. All right. The calculator is just having difficulties because it works numerically rather than symbolically. So the best it comes up with is an approximation of the correct answer. And that e negative blah, blah, blah is trying to tell us 0, just didn't quite get there. If you look at the graph, you could see, though, that it appears that we have equal parts of area above the x-axis as below the x-axis. So there's enough reason to assume that what we're looking at here is accurate. All right, then part C, the total distance. All right, so there's a couple of ways to handle that. We learned in the last video that if we just take the absolute value of a function, we take its negative components and make them positive. All right, so that would take the part of it that's below the x-axis going from pi over 2 to 3 pi over 2 and flip that so that it's above the x-axis. So let me just show you what that would look like. All right. So alpha window on your calculators, I have to do it a different way. Math NUM absolute value. That's actually the same way also on your calculator. If you go in, if you don't remember the shortcuts, it's in the math menu, the NUM, it's option 1. And then I'm just going to select alpha trace followed by y1, just to say that I want the absolute value of whatever I had stored in y1. And you can see that for the parts between 0 and pi over 2 and 3 pi over 2 to 2 pi, it's the same, but the parts between pi over 2 and 3 pi over 2, it got flipped. All right, so quit out of here, math 9, math 9. I'm going to just select alpha trace y1 again. Actually, this time it's y2. So math 9, alpha trace y2, functions in terms of x, going from 0 to 2 pi, and we get 20. If you refer back or think back, I think it was to page 2 or 3, the one where we had all those trig problems, this is really just a scaled up version of a sine cosine graph. All right, so if you know, and I can flip back to it right now. Oops, that's not how you flip back to it. Here, let me just pull this up so I can do that. That's how you flip back to it. You could see that if we're looking for example, 0 to 2 pi or 0 to pi or whatever, just focusing on the positive part of it, you can see that we have an area of 2 for an ordinary sine wave. The same thing would be true for the positive parts for a cosine wave. So if we know that the total area from 0 to 2 pi in a sine wave is going to be equal to 4, well, this is 5 times that, so 5 times 4 would be 20. So if you know that the total area over an interval for a cosine or a sine wave over the interval of 0 to 2 pi is equal to 4, the net area is 0 for sine, and also for cosine, then there's a lot you could do with that. Right? It does require a little bit of memorization, but it's something. You know, the calculator will do it for you, but this, I think, leads to kind of exposing yourself to different modes of thinking. All right. Numbers 16 and 17 are kind of along the same lines. They just change the context a little bit. So I'm just going to take you through number 15. It says find the geez, I can't even talk. The following is a graph of velocity. The particle starts at 2 when t is equal to 0. All right. Find where the particle is at the end of the trip. So that's the net position. And then the total distance traveled by the particle, that's going to be a total position. All right. But bottom line is we're looking for areas again. All right. So here we're not given defined functions. We could figure them out, but area is still area. So why not just figure out what the areas are? Because I know the area of a triangle is half the base times the height. So the base here is 1, 2, 3 units. It's going by ones. The height is also 3. So it's going to give me 9 halves. Area of this triangle, half the base of 2 times the height of 3 is going to be equal to 3. Both positive. Area of a trapezoid, different story. 1/2 the height, which is -3, times the length of the first base, 1, 2, 3, 4, 5, plus the length of the second base. So 1, 2, 3. So it looks like, so 8 divided by 2 is 4, so -12. All right. So we're starting off, the particle starts off at x equals 2. So I already have a starting location. So for A, 2 plus 3 minus 12 plus 9 halves. And for B, same stuff, except -12 becomes +12. All right. Oh, and I never made it positive, so there we are. All right, so just got to crunch those numbers and we're good. So 2 plus 3 minus 12 plus, I'm going to write it as 4.5. So -2.5. So at the end of the trip, this figure, whatever this particle, lost 2.5 units of position. So it took a few steps forward, a few steps back, a few more steps forward, a few more steps back, and at the end of the trip, it was 2.5 steps behind where it started. All right. But actually, I guess it would be 4.5 steps behind where it started because it started 2 steps ahead of position 0, or where it would start, I guess. But it did take a total of 21.5 units worth of steps. Right? So it had some substantial movement to not really go too far. All right. So that's where I'm going to leave it because the next set of pages go into a different part of the unit. I think you can handle the problems that follow because they have an initial amount. They have some information related to derivatives.